I'm Chen Wang, currently a postdoc at Harvard Medical School, the Department for Biomedical Informatics. And today I'm very happy to share with you about my research on interpreting and steer AI with interactive visualizations, and which I think is a really important way to help us moving from powerful AI models to more usable and useful AI applications. So to start with, I do not need to emphasize it again that we are living in the age of AI, but I want to clarify that AI is not just an algorithm problem. We cannot talking about AI without its relation with humans who are living in the real world. The core important question about this part is how users can use AI to complete the desired tasks easily and efficiently, which I call it as usable and useful AI applications. So you can see there are three main components here: the domain users and the AI models, and also the desired tasks. An AI application is as important as developing advanced AI models. AI has provided unprecedented opportunities for humans to analyze and generate insights from extremely complicated and large-scale data, which has enabled the fundamental changes and extensive upgrades across many domains, especially in biomedical applications such as drug design, clinical research, biomedical diagnosis, and healthcare support. I really like this sentence, so I put it here. Even if we were to make no further progress in the next decades, developing existing AI algorithms to every applicable problems would be a game changer for most industries. And I really think this is how important the application of AI should be. Even though very promising, AI applications can be hard to achieve. It can easily went wrong and leading to trust issues and unexpected errors. In a survey, half of the US doctors said that they are anxious about using AI-powered softwares, and this anxiety comes for a reason. Epic, which is the US largest electronic healthcare vendor, has several AI algorithms in their systems that are delivering inaccurate or irrelevant information to hospitals about the care of patients. So, why usable and useful AI applications is hard to achieve? Let's think about the two sides of an AI application. The one part is the capabilities of AI, and the other part is the need of users. One main reason for the challenging of AI applications is that those two parts are usually mismatched. Let's take in the drug development as an example. When people are talking about AI model to design drugs, of course, they need to customize the model and the data set for the specific problem. But still, this model is designed and evaluated on an abstract task, and that is a binary classification problem. They just classify whether the drug can be used or cannot be used for a certain disease. But if we are looking at the real-world complicated tasks, the users need to know more about this problem. They need to know about the biomedical pathways about this drug. They need to understand the medical histories of the patients, and they also want to understand how this drug is used with other drugs. And as a result, to achieve AI applications, we need to fill the gap between the capabilities of AI and the needs of the real-world users. Filling this gap requires the joint efforts of both the AI developers, the user interface design, and also a better understanding of the real-world users. And in my opinion, interactive visualization is the best way to address this challenge. User interface is an effective way to put together different resources of information and allow users to interpret and interact with those information. I created interactive AI tools that combine visualization with explainable machine learning. And specifically, I closely collaborate with biomedical experts and use these applications as a test bed to evaluate how can we better support the AI applications and how can we better understand the users and develop useful and usable tools. Now we have say visualization is a really promising way to address the challenging of AI applications, but still feel the gap between users and AI is like a further term. How can this be achieved? Where the human-AI collaboration is a relatively new and underexplored field. We're actually familiar with communications between humans. In effective human communication, instead of just listening to others about their decisions, we first receive information from them and then interpret this provided information and then give them feedback when there is disagreement or misunderstanding. And each step is built upon the success from previous steps. Let's take an example about a doctor wants to seek suggestions from another doctor about the diagnosis of a certain patient. Instead of just asking the other doctor about his diagnosis, they need to some explanations and extra information, such as this diagnosis is made because of the results of test M and test N. And then the doctor is able to make his own interpretation, such as, all right, the result of test M indicates something like blah, blah, blah. And then he's able to provide feedback when there is some disagreements. So he might say, but the result of test N can be linked to another disease. Similarly, we can think AI as an assistant whom we can turn to for help and suggestions when we solve a problem or make a decision. For useful and useful AI applications, we should support similar interactions between the AI and the humans. I would say one factor contributing to the popularity of ChatGPT is its ability to offer an interface between humans and AI using natural language. But as a visualization researcher who believes that one picture is worth 1,000 words, I focus on the visual explanations and try to provide interactions through the way of interactive visualization. Specifically, my work from three aspects about this human-AI communication. First, apart from just give users prediction results and some summary statistics, such as accuracy, I present users more information and explanations about the AI for the desired tasks. Second, I help users to interpret those explanations and generate meaningful and actionable insights. Third, I enable users to provide feedback and address disagreements and unclear explanations to help them better improve the human-AI communication. These three aspects form the main themes of my research, and in my previous study during both my postdoc and my PhD studies, I have developed a set of studies around those three topics. And today, my talk will focus on three studies, focusing on the interpretation and feedback stage. The first one is a design study where I discussed human-centered considerations into the design of explainable AI tools. And the later two are more visual analytic systems that I developed algorithms and interaction mechanisms where I incorporate human feedback into the refinement of AI models. So first, let's talk about the interpretation of AI explanations. One thing I really want to emphasize here is that providing users explanation is not the same thing as help them interpreting and generating insights. In an ideal world, people hope that a model will become better if we can provide some explanations. The user will trust the model more and they can better collaborate with it and make and perform tasks more accurately and confidently. But that is not the truth. AI explanations can be useless and if not harmful. Here is an example. Attribution-based explanations explain a prediction by highlighting the most important regions in the input data. However, these studies show that these widely used explanations cannot help users identify defective models. But this familiar do not mean that explanations are not usable. For example, where attribution-based explanations are criticized for the classification of nature images, it is actually a very useful technique in regulatory genomics by identifying related genomic locations and helping people decode the genome functions. In other words, which explanations work or do not work is extremely data type and application domain specific. So, given a specific problem, how can we select and present explanation that users can better interpret and generate actionable insights? If we imagine that we have a toolbox filled with various explanation methods, how to choose and select the right one from all those existing explanation methods? I try to answer these questions by extending the nested model for user-centric XAI and conducted a design study on graph neural network-based drug repurposing. So here are some general background about this study, but you do not need to be afraid. It's like a very user-friendly introduction. So I focus on graph neural network in drug repurposing as a test bed to help people better investigate this question about how to interpret AI explanations. And the input data is a knowledge graph where node indicates medical entities such as drugs, disease, proteins, and the edges represent the relations among those nodes. The GNN model tries to predict whether an edge exists between a drug and a disease, that is, whether an existing drug can be used for a new disease. And by identifying new therapeutic use of an existing drug repurposing can significantly reduce the cost and the time in drug development. But however, due to the critical nature of biomedical domains, the domain scientists need to assess and validate the AI predictions before they conducting downstream evaluations, which is often very expensive. So at the first glance, this is a problem about explaining graph neural network models. And many explanation methods have been proposed, but it's important to note that they are not equally usable for the user tasks. If we just simply select and visualize one explanation, for example, if we just visualize the one with the best numerical scores, we cannot guarantee that the users has achieved all the requirements they have. As a result, how to select adopting and presenting useful applications is a non-trivial task. Recent studies have investigated the integration of XAI considerations into the user interface design. However, they are designed for general users and provide little consideration about the visualization design. And to fill this research gap, I incorporate a diverse set of user-centric XAI considerations into the design layers of our visualization process based on a literature review and our collaboration with domain experts. Here, I will give two examples about how we incorporate design considerations into the design of an AI tool. So the first thing we'll think about is the format of AI explanations. There are definitely more than one way to explain a prediction, and which format exists and how to choose one from all the existing explanation formats. So in terms of the graph neural networks, I identified three common visual presentations from a survey of the current studies, and they are graph-based, path-based, and node-based. So here is the example about how the same prediction that a drug repagilide can be used for Alzheimer's can be explained in three different explanation formats. And in the node-based explanations, we are trying to explain it by highlighting the most important neighbor nodes around the drug and the disease. And similarly, in the graph network for this drug, this disease and this drug, we try to highlight the most important subgraphs around this drug disease query. And in the path-based explanation, we try to highlight the important paths that are connecting the drug and the disease. And here is how we generate the predictions and explanations, but I will not go to details here. And then we compare those three different explanation formats with how a domain expert would reason about a drug indication. And then we can find that the path-based explanations is more similar to how the domain users would reason about a drug indication, and then we implement it in the XL tool. Another important factor is the granularity of explanations. So should we explain the explanations for the whole AI model, or should we just provide explanations for a certain prediction? I found that users desire not only local explanations, that is, an individual path that explains a certain drug prediction, but also group predictions, and that can explain multiple similar drug predictions at the same place. So for example, here we use MatPath as a group explanation, which consists of the type of node and the relations. So you can see this MatPath can summarize different explanations. We also find that global explanations are relatively less interesting to the users. By putting all those design considerations together, I propose a mat matrix design, and you can see here each column is a drug, and each row is a MatPath that summarizes a group of individual paths. And the cell indicates a number of individual paths, and users can click it to investigate further details. So here is a brief use case of the proposed visualization. You can see here the users first choose a disease, and then the prediction and the explanations are updated and visualized. In the embedding view, it shows the embedding of all the drugs in the knowledge graph and highlighted the predicted drugs. And in the MatPath view, it tries to provide explanations of those predictions. We can see that the similar drugs forms clusters in the embedding view, and here is a cluster of anti-diabetic drugs. And this is consistent with the current understanding about the relation between Alzheimer's and diabetics. And we choose one drug from it, repacklight, to do further analysis. So first, users can expand or collapse and hide or unhide explanations to better organize them. And then we can say that repacklight is predicted partially because its target protein is associated with the Alzheimer's disease, but also because of ibuprofen, a painkiller which shows a relation between the treatment of Alzheimer's. We can also say that similar drugs share similar explanations, and all those explanations can help users to better access the AI predictions and understand how promising a drug candidate can be. We further conducted a user study and expert interviews to evaluate this visualization tool and the design process. Here, I only report the results to demonstrate why choosing the right explanation is very important. So first, we can see here the path-based explanations help users to perform the tasks more accurately, confidently, and quickly. But we can also see that a poorly designed explanation is not necessarily better than non-explanation baseline. And that really demonstrates visualization is an important but previously often overlooked aspect of the AI applications. And that's the first time that we find for the scientific application of AI, the design of visual presentations can make a huge difference. And these findings and these tools make the community very exciting, and we have got awards from both the machine learning community and the visualization community. And this tool is also used by people around the world, and that's like the use data about this tool last month. But of course, we need to admit that there are no perfect AI models and there are no perfect explanations. For example, the hidden MatPath here didn't really make sense. It tries to explain the prediction of a disease because the protein of this disease and the protein of the drug are located in the same anatomy, which is more like a association rather than a causality. In the current tool, we allow users to hide and collapse explanations to provide a workaround and to organize explanations and remove unneeded ones. But how can we actually use user feedback to steer the AI model and to obtain more accurate predictions and explanations? That moves to the third part of my research about steer AI models. And more importantly, since the user feedback always relies on an accurate interpretation of explanations, we want to ask, can AI explanations enable users to interpret and steer AI at the same time? To answer this question, I reflect which type of human knowledge can be used to interpret and steer AI. And one common used human knowledge is a human's knowledge about classes, such as different types of fruits and the cat with dog image classifications. And in Polyphony, we try to help users to better employ their knowledge about classes to interpret and steer AI in the single cell annotation. So let's go back to talk about the classification. AI can understand classes based on the similarity to the items in the training dataset. And this similarity can also be used as an intuitive explanation about the explanations that about the predictions that the AI model make. And the AI's ability to do classifications is widely used in many applications. And Polyphony looks at one specific application, annotating cell types in the single cell analysis, which is a very new and promising technology that enables the investigation of human body at the single cell level. However, if we directly apply AI models for cell type annotation, it can be problematic. In an ideal world, we imagine that the labeled data and the unlabeled data looks very similar, so that the model trained on the unlabeled data labeled data can be used to predict the unlabeled data and generate accurate predictions and explanations. But the thing is, in real world, the unlabeled data sometimes looks very different from the labeled data, even though they are belonging to the same type. So, for example, in the single cell analysis, because of those cells that come from different experiments, even though they are the same cell type, they look very similar. So here is a demonstration. All those points with the colors, they are already labeled and the color indicates the cell types. And all those points without colors, they are the new data. And if we just project them into a 2D space, those view data do not overlap with any of the existing points, which indicating they didn't look similar to any of those existing cells. And that can be very confusing for the classification model to make a prediction. Of course, there are some algorithms try to address this issue, but the challenging part is that I cannot tell the technical variance from the biomedical variance. So a technical variance means that those two clusters are indeed the same cell type. They just comes from different experiments, so that they look different. And a biomedical variance means that they are indeed different cell types. That's why they look different. As a result, human inputs are needed to help this process. In the current workflow, people usually run automatic annotations first and then ask the humans for validation. But can we make this process more efficient by involving human knowledge in the annotation process? One widely used method in active learning is to ask humans to annotate the labels during the classification process. So usually they ask the users to annotate the items with the lowest confidence score. But previously, studies have showed that users do not want to be treated as an oracle that simply label the individual items one by one. And also, they require transparency about the AI system to help them provide more accurate feedback. Therefore, I propose interactive anchors to enable simultaneous AI interpretation and steering. An anchor indicates similar clusters across datasets. So, for example, here is one anchor. It consists with two clusters. This one unlabeled this one unlabeled, and this one is labeled. And we call it an anchor because the prediction of those unlabeled cells is anchored and based on the type of these clusters. And this is another anchor. So Anchor provides a very intuitive way to help users to interpret the AI predictions. And also it allows users to provide feedback. So the users might say, these anchors make sense to me, and I indeed believe those cell clusters is the purple type. And they might also reject this anchor because they do not think these cell clusters is the orange type. And based on the user feedback, the models can be refined and make better predictions and explanations. So you can see now we are able to explain and predict other cell types more accurately. Polyphony is an interactive AI tool for single cell annotation that enables users to interpret and steer anchors. So first, to generate anchors, we identify clusters in the labeled data set and then calculate a matrix to compare the similarity between each unlabeled items and the clusters in the labeled data set. So you can see anchor is generated by pairing the clusters with the most similar unlabeled item. After generating the anchors, Polyphony offers 3 different views for users to interpret those anchors. So you can see the first in the embedding view, each anchor is represented by a cluster of points and a cluster of grids. Those grids indicate the already labeled cell types, and those are like the clusters from the unlabeled set. And this link indicates connect those 2 clusters, and we can observe the quality of this anchor based on the length and the width of this link. Also, we rank all the anchors based on a set of scores, and for each anchor, we show the shared features between the 2 clusters. And in this specific case of single-cell analysis, we show the expression level of the marked genes of those 2 cell clusters. And by interpreting the recommended anchors, users can steer the AI by refining, confirming, adding, and rejecting anchors. So first, we can say here users choose an anchor with a relatively low ranking, which means this anchor has a relatively low quality. And then it refines this anchor based on the expression level of a shared feature. And users can also just delete an anchor if they think it doesn't make sense, or add new anchors based on their understanding about the data set. And the user refinement will be used to improve the model, and we can say on a human pancreas data set. After user refinement, those points and the grids are better aligned with each other, which indicate improved quality about the data integration, but also the explanations and the predictions. So here are some quantitative evaluation that shows that Polyphony can improve the annotation accuracy. The importance of Polyphony goes beyond just improving annotation accuracy, and to the best of my knowledge, it is the first human-in-the-loop annotation framework, showing a new possibility beyond the previously end-to-end methods. And we can see here, instead of just accepting all the recommended anchors, the user involvement achieves large performance improvements by only selecting the high-quality anchors. So to sum up, through interactive anchors, Polyphony successfully help humans to improve the single-cell annotation and interpretation by using the knowledge about the classes. But human knowledge can be more complicated than those separated classes. For example, in each clusters, in the right side is the image pictures from the breast cancer specimens. And they all look very similar, and if we project them into a 2D space, there's no clear clusters in this 2D space. And the result is really complicated for humans to interpret and explore this data set. As a result, we need to support more complicated human knowledge in AI interpretation and steering. And in Java, I investigate how humans' knowledge about concepts can be used. So first, what is a concept? A concept is an abstraction that can be used to describe the characteristics of items, such as the shape and color and the texture. So, for example, a zebra is related to the concept of horse, stripes, and grass. And a concept can also be shared by multiple classes. As a result, concept is a more flexible and transferable form of knowledge than classes. And if we go back to the example of the breast cancer specimens, if we can arrange all the items based on the tissue density and the tissue color, we're able to organize all the items in a transferable and interpretable way. Concept can be learned by an AI model and serves as a human readable explanations. For example, previous studies have demonstrated that there is a decision boundary in the latent space that distinguish items has a certain concept and items that do not have a certain concept. But this difference exists in the latent space and they must be extracted and presented to the users. This entangled representation learning is a promising method to achieve this goal. And the model here tries to disentangle concepts and encode them in separated latent dimensions. So for example here, through an encode and decode structure, an image is represented by a latent vector and the value of one dimension is related to the angle of human head. You can see here by changing the value of this dimension, we can see that the head angles gradually changed in the synthesized images. And therefore, this model can learn the concept without human annotations, and it also shows the users what a concept exactly looks like. And for example, instead of projecting all those images about the human faces into a 2D space, which is hard to interpret somehow, we can organize them using the concept about the human angles, or like the value of the second latent dimension. Again, even though very promising, those concepts cannot be directly applied due to the mismatch between humans and the machine learning models. So for example, here we can say that the model confuses the angle of the head with whether a part of the face is covered by shadow. And here is another example. And to be honest, I first noticed this mismatch by browsing all the images one by one, and I bet no one wants to do that. It's just very efficient and time-consuming. So to use concept for the visual exploration, it is needed to present the concepts in a way that users can easily interpret, identify the potential mismatches, and provide effective feedback. Java is proposed to help users use concepts for visual explorations by supporting the interpretation and the steering of concepts. I will demonstrate the functionalities using TAD, which is topologically associated domains, is a region of interest in the genomic context matrices. But you can just think each TAD as a heat map visualization where the visual appearance represents some biological events. And that's all you need to know about it. So to interpret the concept, the most straightforward way is to say the synthesized images associated with each concept. And here, each row represents a latent dimension and which might relate to a potential concept. And we also rank all those dimensions through a Sinin score to facilitate the visual exploration. We can see here there are three concepts that are meaningful and are ranked high. And let's take a closer look. But you can see like how each concept looks like through these synthesized images. Those synthesized images provide an intuitive way to interpret concepts, but as shown in the head angle example, they can hide some imperfect or inaccurate concepts. As a result, Java also allows users to interpret the concept through items using interactive piles. So first, what is interactive piles? Interactive piles is inspired by the efficiency of physically piling for grouping and summarizing items. So for example, we can pile a bunch of items and show a preview for each items, or we can just generate an average summary. And so you can see here is a pile of the tags, and based on the preview, we can say that there are similar items, and there is another pile, and we can easily identify there are several abnormal items. And the Java provides a set of different ways to group and piling items, but I will not go to details here. So we can say interactive piles can reveal the concept mismatch between the humans and AI. And here, those abnormal items shows the AI model confused two concepts, the diagonal thickness and the nested structure. And it is important to note that this mismatch would be hidden if we only look at the synthesized images, which unfortunately is widely used as the only method to present concepts in the disentangled representation learning. Since we have identified another dimension related to the diagonal thickness, we can use it to separate abnormal items and refine the concept. So you can see here, I first use, wait 1 minute. Yeah, I use a nozzle to select all those abnormal items and move them to the left side. By doing that, I'm turning the model that the concept about those items is incorrect and they need to be improved. And this is just one example of the user refinements supported in Java. After user refinements, the original encoders and decoders are fixed, and an additional concept adapter is initialized for the dimension to refine the learned concept. The evaluation shows that the proposed method improves the quality of the concept compared to an active learning baseline. And by learning the concept, Java enables a more interpreted visual exploration than the commonly used dimension reduction method. And now let's go back and look at the breast cancer specimens. So again, if we just project them into a 2D space, it's hard to interpret, it's hard to explore. So Java allows users to organize items using two concepts that are identified and annotated by the users. And yes, there are tissue density and the tissue color. And also by adding labels of each items, we can see there is a strong correlation between the presence of the cancer cells and those two visual concepts. So you can see this part of the tissues are mostly negative, and this part of the tissues are mostly positive. To better understand this correlation between the cancer cells and the visual concepts, we filter items to investigate the confidence but false negative predictions. So here, by click those bars in the histogram, we filter out items that are associated with and we can see that the remaining items are mostly loose purple tissues, and they are mostly likely fat tissues surrounded by cancer cells. And such an observation leads to human-readable descriptions about what hard example for cancer classification model looks like. And those conclusions and observations are really important to help users better diagnose, refine, and collaborate with the cancer classification model. And to sum up, by enabling users to interpret and steal the concept-based explanations, Java provides more accurate concepts and enable more interpretable and flexible visual exploration. Then, by imitating the human communication process, MyStardy creates interactive AI tools to help people to better interpret AI models, generate insights, and explore the data. Specifically, I investigated the design considerations for creating interactive visual explanations, and I introduced 3 specific visual explanations in detail, which provide explanations, enable intuitive interpretations, and also support effective user feedback. The proposed visual explanations enable higher accuracy, confidence, and speed on the human-AI collaboration, and it also helps identify insights that cannot be extracted using the existing methods. My studies also have impact beyond publications. Most of the tools are open sourced through online documentations, interactive demos, and GitHub repos. And they are used by my collaborators and many real-world users that I haven't met before. And Gosling, which is a genomic visualization toolkit, has been downloaded more than 12,000 times in the past 2 years. And also, I'm fortunate to be covered by some media such as Nature, Technology Features, and MIT News. In the coming years, I will continue my pursuit for useful and usable AI applications. Specifically, I'm eager to explore these 3 directions, which are built upon but also greatly extended my previous research, especially those 3 clusters. So first, safeguards for interactions. As AI is not perfect, humans is also not perfect and tend to make mistakes. It is very risky if we just use those human feedback to steer the AI model. To solve this question, we need to understand when and why do humans give biased and inconsistent feedback, and provide visual techniques and explanation design guidelines to help people make accurate and informed feedback. We also need algorithms and crowdsourcing mechanisms to identify those inconsistent feedback and minimize the negative impact. Second, towards multimodality. So far, my research mainly focuses on the single modality, and there is usually one type of data, and explanations are presented in a single format, which is visualization. However, multimodality can promise a more comprehensive way to analyze data by highlighting the patterns and the relationships that might be missed by using just one single modality. And also, we can expect a more effective communications between AI and humans by going beyond visualization explanations, and such as we can think about the combination between visualization and natural language. This is a very exciting direction, but we only have a very limited understanding. Second, AI for science. How can we help people better generate hypotheses and validate these hypotheses with AI explanations? My studies has helped users to interpret and steer AI explanations, mainly based on the knowledge about this domain, and several success has been made in the biomedical applications. But nowadays, the advance in AI has promised to generate new knowledge that the humans don't know before. So the AI might have some hypotheses about a new approach to diagnose a certain disease. And currently, we still lack a method to systematically generate and validate those hypotheses from AI explanations. At last, I would like to thank my fantastic mentors and collaborators for the hard working, for the valuable feedback, and for the insightful debates. And also, my cat and Harvard therapy dogs, they made significant contribution to my research by providing tremendous emotional support. And that's all. Thank you so much for your listening, and happy to take your questions and comments.